So we are now on the last section of vibrational motion or simple harmonic motion. That is energy in simple harmonic motion. Why do we have to use this? So far we have analyzed vibrational motion using the force approach, where we apply force to cause an opposite displacement, and that force is the restoring force coming from the spring. And the problem with that is that forces is not constant. So in order to stretch, let me show you, in order to stretch or compress a particular spring mass system, we have to apply a force that causes a displacement, which is what? Which is parallel to it, and therefore there is work being done on the system. If there is work being done on the system, then there must be another physical principle that we could use that can easily be understood, and that is energy. So we will just treat this an isolated system. We neglect friction in this scenario. So if I compress this spring, there will be what kind of energy? There will be elastic potential energy. And when I release this spring, you would notice that the velocity increases, therefore it changes into another type of energy, which is kinetic. And if we look as it passes its equilibrium position, the velocity is increasing from 0 previously here. So the velocity here is at its maximum. So the kinetic energy here is at its maximum. And then, given that the restoring force is at its minimum, the velocity will move that object, undergoing change in the restoring force. So we're going to analyze that. So let's take a look at that piece by piece in order to analyze energy in simple harmonic motion. So let's take a look at this particular setup in here. So let's go back to it. So we compress the spring. So given that, we have an energy that is equal to 1/2 k times the amplitude squared, because amplitude squared is proportional to the displacement. So we could say energy, so you can write that as U, elastic, which is equal to 1/2 kx squared, knowing that the maximum displacement is either at its positive or negative amplitude relative to the equilibrium position. So we notice that the velocity there is 0, but then the restoring force is at its maximum. Therefore, if the restoring force is at its maximum, which is directly proportional to the acceleration is its maximum as well. And if the acceleration is at its maximum, the velocity there is at its very minimum, which is 0. So the restoring force will cause a displacement opposite, and as it moves and hits the equilibrium position, the velocity there is at its maximum. And the kinetic energy bar is at its maximum. And as it passes through the positive displacement, it goes back to that particular energy, which is the amplitude squared, and then goes back again, passes back to the equilibrium. Now this is now a combination of the two energy. So given that, we can have the energy equation for a simple harmonic motion, which is, so the energy before or initial is equal to the energy final or after. So the energy before would be 1/2 k a squared, and then the energy after, and V to make one cycle, V 1/2 kx squared. So if we're going to find the velocity, either the maximum velocity or the velocity at a certain point, we could use this equation to be able to find it. So let's use that. We could factor out the 1/2 in here, and then we could isolate v squared. So if we isolate v squared, we would end up with this equation. And also we could derive some equations relative to that. So we can have v is gonna be square root over k over f square root a squared minus x squared. So that's another one. We could also use this equation, since this one is related to angular velocity. So the angular velocity plus or minus depending on which sine curve it's using. It can be a squared minus x squared. That's something given. So another thing that we could also use is to find the maximum velocity here. So what will be the equation to find Vmax? So I'm sorry on those errors of my pen. It's getting older. So in order to find the Vmax, we can factor out 1/2 in here. So we could find k over m times the amplitude squared times the amplitude. Sometimes I would write it this way so that you know the mathematical process. So get the ratio of this values in these quantities in here, get the squared, multiply it with the amplitude. Because sometimes student would mistakenly get the ratio of this, multiply with the amplitude, and get the square root. So that's how you deal with that first. So I think this is easy to remember. Again, you do not need to memorize this. This is just a way for you to be able to find the velocities and use this to be able to solve some problems. So that is how we look at energy in simple harmonic motion. So let's say we try to stretch this spring twice the original. So let's practice this concept in here. So what will be the energy of the system? Proportional to the square of the amplitude. So therefore, if we double the amplitude, because we double the displacement, so we will have 2 amplitude and then squared, it will be quadrupled. So the energy will be quadrupled. Okay, so let's answer B and C. So for letter B, if we look at the amplitude, it's related to the velocity. So if you double the amplitude, you also double the velocity. So for C, what will be the maximum acceleration of the mass? Given twice the force, second law is directly proportional to the acceleration. So the acceleration will be twice and also directly proportional to the displacement. So this is a way of applying the concept of energy to simple harmonic motion. So now let's have one more problem here. So let's take a look at this. So you have a 0.5 kilogram block connected to a horizontal spring. So if we will illustrate that, so there is the spring and there is the block moving across a horizontal surface that is frictionless. So we are asked to find where is the acceleration at the maximum. So if this is the equilibrium position, the maximum acceleration will be relative to the equilibrium, either positive or negative. So this is where the acceleration is at its maximum. So acceleration is at its maximum there. So if we look at the picture here, the acceleration is at maximum here, acceleration is maximum here. Now, where is the acceleration? 0. Acceleration 0 is at the equilibrium. Why? Because acceleration is directly proportional to the displacement. And we also saw that in our warm-up activity. Now let's answer another question. Letter B, in this case, where is the velocity maximum? So let's illustrate that again. So you have the spring and the object. The velocity maximum will be at its equilibrium position. Velocity 0 is gonna be where the displacement is at its maximum, negative, and then positive. Velocity there is equal to 0. Acceleration there is at its maximum. Given the restoring force will be at its maximum there as well. And then the stretching force will be maximum there as well. And then acceleration here is 0. So how do I calculate the maximum velocity? We could go back to the equation we have a while ago that we derived. So you have this. You could use this equation for velocity. So let's choose that. Or we can use this or this one. Okay, it's right here. Alright. I'll pause and give you yourself time to. Or you can also apply this concept. So, and then square the value of the velocity. So your velocity should be, so square the velocity. Your velocity should be 0.19 meter per second. So you can use this or you can use that. Now let's answer this. What will be the total energy? So total energy or K total is equal to 1/2 K A squared. And you plug in the values. What will be your total energy? Or rather, E here, total energy would be, you should get 9 times 10 raised to -3 joules. Now what about the period? How do we find the period and the frequency? So period for a spring is equal to 2 pi times the square root of the mass over the spring constant. So you should get an answer that is approximately 19.9 seconds. And then we know that period is the reciprocal of frequency. Frequency is gonna be 0.05 or hertz, or vibration per second, oscillation per second. So that's pretty much sums up the energy in simple harmonic motion. There will be times that you might be asked to find the velocity given the angular velocity. So that's another equation that we could use. So if we go back to velocity is equal to squared K over M times the square of the amplitude minus the square of the displacement. And we can look at that as V is equal to square root of K over M times square root of this. This one, guys, is technically the angular velocity. So we can, you can find the derivation on this, but just take note of that. So it's plus or minus in terms of the position, which we could now also plug that in as V is equal to angular velocity square root a squared minus x squared. You may be asked to find the acceleration. So I've mentioned the acceleration in our previous discussion. So just use that concept in terms of the maximum acceleration. So you could use the Hooke's second law. So you can have that and then apply that, which is negative k over m x squared. So x squared, you could replace that as k over m a squared, so you could determine the maximum acceleration. So this is the easiest way to get the acceleration, although there's another one too, which is 2ft squared times a. So that's another equation to find for maximum acceleration. Those are the easier one. You don't need to know how it was derived using derivatives, because that's beyond the scope of algebra-based AP Physics 1. So just take note of this, and always just apply the concept of conservation. You should be fine. So you could just go back to this. If this is so cumbersome on your end, just calculate in terms of energy concept. And that's pretty much it.